Hello again. We'll pick up where we left off in section 5.1 on the second page of the notes. We had just defined an angle of central angle of measure 1 radian, and then said in general that we can determine the measure of a central angle in radians by dividing arc length by the radius. The next thing we'll look at, it follows that if theta represents exactly one complete revolution, then theta equals 2 pi radians. Let me show you how this follows from the formula or definition theta equals s over r. If a theta represents exactly one complete revolution, so in other words, we're talking about an angle. This is our central angle, one complete revolution. Then the arc length is the entire circumference of the circle. So what we can do here is say, let's let S, the arc length, be the circumference C, and we know from geometry that the circumference of a circle is 2 pi times the radius. Then it follows that the radian measure of the central angle by our result above is S over R, which in this case is C over R, but C is 2 pi R. Divide that by R, and so you can see that the measure of the angle is 2 pi radians. Now notice this is 2 pi radians, but we don't really have to use a symbol. We can just write 2 pi, because actually the angle measure is unitless. There are no units that we have to associate it as we would with degrees. So it then follows that 360 degrees, which is one complete revolution in degree measure, is equal to 2 pi radians. Now pi is about 3.14, so 2 pi is about 6.28. So we could also say that one complete revolution corresponds to an angle of a little bit more than 6 radians. We could also say, by dividing 360 equals 2 pi, dividing both sides by 2, 180 degrees equals pi, or approximately 3.14 radians. As I've already mentioned, since radian measure is actually unitless, we're allowed to drop the word radians altogether if we wish and just write 180 degrees equals pi. And without any symbol next to the pi, it's understood that that represents radian measure. It's pi radians. Now this last equality, 180 degrees equals pi radians, is very useful in converting between degree and radian measure for given angles. So we can use the equality above, that is 180 degrees equals pi, to form one of two unit fractions. A unit fraction is a fraction whose value is equivalent to 1. We can either write 180 degrees over pi or pi over 180 degrees. Now neither of those fractions looks like it has a value of 1, but that's exactly what its value is, because the numerator and denominator represent the same angle measure, just in different units of measure. So both of these fractions have a value equal to 1, which means that if you multiply any quantity by one of these two fractions, it will not change the size of the quantity, since you are simply multiplying by 1. Let's show how this would work with a few examples. Convert the angle from degrees to radians, 60 degrees. What I might suggest you do here is start by writing this as 60 degrees over 1. And since we're trying to convert to radians, we're going to use this second version, pi over 180 degrees. We're going to multiply by pi radians over 180 degrees. The reason we choose the second version is we want to cancel degree measure and replace it with radian measure. And notice that you're going to be able to cancel degrees with degrees by putting 180 degrees in the denominator. All right, if you multiply these two fractions, it's 60 pi over 180. And since 60 goes into 183 times, this would simplify to pi over 3. So the radian, the angle measure equivalent to 60 degrees in radians is pi over 3 radians. By the way, pi over 3 is a little bit more than 1 radian because pi is just a little bit bigger than 3.14, remember. 90 degrees. Okay, this is very similar. Take 90 degrees, let's just write it over 1 to make it look like a fraction. Multiply by pi over 180 degrees. That would be 90 pi over 180. And 90 goes into 180 twice. So that simplifies to pi over 2. So 90 degrees is equivalent to pi over 2 radians. And then our third example is a negative angle measure in degrees, but that's not really going to affect how we do the computation. It's just a negative measure, so it's going to have a negative radian measure too. Right? Negative 100 degrees over 1, multiply by pi over 180 degrees. So let's simplify this to negative, or let's write this rather as negative 100 pi over 180. And we can divide 100 and 180 both by 20. That's their greatest common divisor. And that would give us, in simplest terms, the radian measure negative 5 pi over 9. This could also, of course, be approximated if an approximation would be useful. So let's just show what the approximate value would be using a calculator, about negative 1.75. And that would be negative 1.75 radians, but we don't have to use radians as a symbol or anything. We just understand, because there is no unit symbol, that it's radian measure. So we have exact radian measure, negative 5 pi over 9, or approximate radian measure, negative 1.75. Usually what we're going to want to do is to try to represent radian measure in exact form whenever possible, and only use approximations if it's really necessary to do so. Let's look at example 2. We've converted angles from degree measure to radian measure. We can certainly go in the other direction, starting from radian measure and converting to degree measure. And as you might guess, all you have to do is flip the unit fraction over. Put degrees in the numerator and the equivalent radian measure in the denominator, and just multiply. You're still multiplying by 1. You're just changing the units. 6 goes into 180 30 times. The pi's cancel, and we obtain 30 degrees. Pi over 6 is equal to, pi over 6 radians is equal to 30 degrees. Negative 3 pi over 2, it's going to be very similar. Multiply by 180 degrees over pi. Okay, the pi's are going to cancel as before. 2 goes into 180 90 times. 90 times 3 is 270. We're left with negative 270 degrees. The last one looks a little unusual, but this is actually not such an unusual thing to see radian angles measured in radians not expressed in terms of pi. Pi is commonly encountered because, after all, radian measure is defined in terms of circles, and pi is the most important thing associated with circles when it comes to mathematical constants. But we can have angles measured in radians just in terms of, say, an integer value like 1. And what we're going to do here is exactly what we did in the other examples. We're simply going to take the given radian measure, in this case 1, and multiply by 180 degrees over pi. that means the exact radian measure, or excuse me, the exact degree measure here is 180 over pi degrees. But you know, when we're working with degree measure, we usually don't represent angles in this form, 180 over pi. We'd prefer here definitely to represent it in decimal form. So to the nearest tenth of a degree, if we do 180 divided by pi on a calculator, what we would see is it's approximately 57.3 degrees. So I mentioned previously that if you look at an angle of where the intercepted arc is, its length is identical to the radius, then it looks like about a 60-degree angle. This is showing that actually 1 radian is a little bit less than 60 degrees. It's a little bit more than 57 degrees. So it's useful just to keep in mind that an angle of measure 1 radian is approximately a 60 degree, has a 60 degree measure in degree measure. Just a little bit less than 60 degrees. So 1 radian is significantly larger than 1 degree, obviously, as you can see from this example. Moving to the next page, the most important degree-radian relationships are summarized in the table below. Some of these we've already encountered, but let's just go through the table. 0 degrees is the same as 0 radians. 30 degrees, we did this computation earlier, I believe, pi over 6 radians. 45 degrees, pi over 4 radians. 60 degrees, pi over 3 radians. 90 degrees is pi over 2 radians. 180 degrees is pi radians. We've already talked about that. 270 degrees, 3 pi over 2 radians. And then finally 360 degrees, we talked about this as well, 2 pi radians. So you will need to know these relationships. These are relationships that you should not have to think too hard about, that basically you should memorize. You can also see in relation to a circle where the angles would be located, and again the correspondences between degree and radian measure. One of the things that's interesting about radian measure is that for other angles beyond the acute angles, the angles 30, 45, and 60, which are the so-called special angles from geometry, you see that when you have angles associated with these special angles, that their radian measure is in terms of pi over 6, pi over 4, or pi over 3. For example, 150 degrees, which has a radian measure of 5 pi over 6, is associated with an angle of 30 degrees. And 30 degrees is pi over 6 radians. So you can see that an angle associated with a 30-degree acute angle has a radian measure that is a multiple of pi over 6, which is equivalent to 30 degrees. So the angles, these are referred to, these acute angles I'm referring to are called these acute angles are referred to as these are called reference angles. I had to pause for a second. I couldn't remember the term. Forgive me. This happens to me more often than I'd like to admit, I'm afraid. These acute angles like the pi over 6 I'm showing you are called reference angles. The term didn't come to me for a second. We'll talk about those more later. I don't want to start the whole video over because of my brain freeze there. So anyway, you need to start to get familiar with these correspondences between degree measure and radian measure, and especially get comfortable with the radian measure, which most students are certainly less familiar with. We'll continue with the notes in the next video.